So if we scroll back up to black and root, where is it? OK, good. OK, so if we scroll back up to black and root, then black and root of a tree takes a node and colors it black. So what does this do to the black height of a tree? Sorry? Increases it by 1, maybe. So if the root of the tree is already black, then it leaves it the same. If the root of the tree is red, then it increases it by 1. Okay? So we could prove that property. But in fact, we don't even care that it increases it by 1 or not. All we care about is that it takes a tree with a black height and returns a tree with a black height. So what we'll prove about black and root down below is that if you give me a tree with a black height, then I'll give you back black and root of t will be a tree that also has some black height. And the way we'll represent some is with what's called a dependent pair type, or a sigma type, which is written sigma x colon a dot b, okay? Or in Agda, sigma of, it's a little bit funny, backslash x colon a arrow b. Okay, so black and root BH is going to be a theorem that says, give me any tree t and any n, which is a natural number. If t has black height n, then there exists some natural number m such that t has black height m. OK, and if you want to write the backslash and you're getting it's going into the Agda mode, then do a double backslash. So backslash backslash to get an actual backslash. Black and root t m. OK. All right, so what we're proving here logically is give me any tree that has black height n. I will give you back a number m and a proof that black and root of t has that black height. So there exists some m. The reason for the funny syntax on the sigma is that sigma is actually defined in a library. It's defined in the file preliminaries.agda. And this bit here is an anonymous Agda function that's the argument to the sigma. But you can just read it as this kind of dependent pair type. So a dependent pair type, sigma x colon a dot b, has elements a colon a and b colon b with a substituted for x. OK? Good? OK, so let's prove this theorem. We've got a tree. We've got a number. We want to show that we've got a proof that that tree has that black height. We want to come up with this. OK? So the very first thing we want to do is, well, we're trying to come up with an element of a sigma type, right? So we can write a comma in the goal and say, hey, the thing we're going to produce is going to be of the form something comma something, OK? And refine. And then we can look at the type of the second component. The type of the second component says, hey, what you need to do is show that black and root of t has some black height, where the question mark 1 is Agda's name for the type, the thing that goes in the first goal. Okay? So the key thing to note here is that Agda has told us you need to come up with the black height of black and root of t. How are we going to do that? Do we apply HBH node red or HBH empty or what? Yeah. OK. So here's the thing. If you want to prove that black and root of t has a black height, the thing you want to do is look at all of the cases for what T might be. That is, you want to do case analysis or induction on T. And then in each case, you'll be able to show why that particular tree has a black height. Okay? We can't show it in the abstract because we don't know whether to apply it's a red node or it's a black node or it's empty. Okay? We have to pattern match. We have to do analysis on the things we're given. Okay? So we can use Agda to do that by writing in the first goal there. So actually, let's back out of the comma here because the thing we're about to do doesn't work if you've already expanded the right-hand side. What Agda can do for you is it can do pattern matching for you. So if you write a T in the goal and then do Agda to make case, what you'll see is that Agda makes the cases that you would need for that data type. It's a tree. It's either empty or it's a node. Agda puts in those cases for you. Okay? And we can rename the variables here to node of L, C, KV, R. It doesn't pick particularly smart names. Tomorrow we can show you a way to pick smarter names there. Okay. Now let's look at the goal for empty. Okay. So let's put a comma back in because we know it's a dependent pair. Question mark, comma, question mark. Okay. So now the type of the second component there is now empty has a black height. Okay? Why is the type empty has a black height? Well, what we need to show is that black in root of empty has a black height. But black in root of empty computes to empty because Agda has a thing called definitional equality built into it. And the clauses of functions induce definitional equalities. So when you have the function black in root applied to the constructor empty, it reduces to the value empty. And that happens silently. You don't need to mark that reduction in your proof term with a simple or something like that. It just happens. Okay? So Agda has reduced the goal to showing that empty has a black height. Okay? Okay. So how do we fill this in? Well, we apply HBH empty. So if we just refine, Agda will fill it in. And then we can fill in the first component with either 1 or underscore. And in either case, Agda will be happy. OK. So now let's look at the next one. We want to show that node L black KVR has a black height. Okay, so, and we're given that node LC KVR has black height n. Okay, so if you think about it, what are we going to do here? We need to pull some information out of the derivation we're given that the tree with color C has a black height, and use it to construct a proof that the tree with color black at the root has a black height. Okay. So we're going to need to look at this derivation or proof term H, which says that this has a black height. Okay? So before we can look at H, there's two ways to do this. Okay. What do you think? Inversion first? Yeah, okay. Let's do it. Yeah. We're not going to get quite as far as I wanted to, but that's OK. OK. So let's do this. So let's do this. We're going to first take a look at the color. OK. So what we're going to do first is we're going to analyze the data enough that there's only one possible rule that could have applied. And then we'll apply inversion to look at the derivation. So that's the abstract. The specific is, let's case analyze the color and have cases for red nodes and different cases for black nodes. Okay? Now, in the case for a red node, what we have in H is a proof that a red node has black height n. Okay? If we know that a red node has black height n, what must have happened? How must we have concluded that a red node has black height n? We must have applied HBH node red. So if we now case analyze H, then what we get is one case where HBH node red was the rule that applied. And we now have subderivations, HL and HR, which if we look at the types of the things in the context, say that L has black height n and R has black height n. Okay? So we just worked ourselves down to a situation where only one inference rule could have applied. We said by inversion, here are the premises. Now we've got the premises. And now we can fill in the right-hand side. Because if we put a question mark, comma, question mark in the right-hand side, then over on the right, we've got that L has black height n, R has black height n. We need to show that node L black KVR has some black height. How do we do that? Well, apply HBH node black to HL and HR. Okay. And so what we really do is apply HBH node black to 4 underscores, followed by HL and HR. Okay. And we can, yeah, good. Okay? Okay. And then there, that one's fixed. So that's, we could either fill in n or we can just fill it with an underscore. Successor of n, or fill it with an underscore, right? Because the black height that we're returning is 1 more. Okay, so you see what we did there? We took apart the fact that a red node had a black height and put together the fact that a black node has a black height. So notice the funny dots there? Okay, what the dots are doing is they're saying, a dot pattern is saying this argument is forced to be n by typing. Okay? It's saying there's no choice for what this argument is. It must be n. Okay? So when you have that situation, you have to write a dot pattern. We'll see more of those coming up soon. Okay, and now in the black case, what do we need to do? So what we have is that, don't do that yet. What we have is that a black node has black height n. Okay. Before we can take apart, if we want to get ourselves into a situation where only one rule could have applied here, we really want not n, but successor of n prime for some n prime. So let's take a look at what n is, by which I mean let's case analyze n. Okay. When n is successor of n, now if we look at h, then there's only one thing that could have applied. Okay, so if we case analyze h, we know that it's this inference rule, HBH node black, and we know that we have subtrees h and h1, it called them, that say that L has black height n, R has black height n, okay, and then we can put it together on the right-hand side. Okay? Yeah. Oh, good idea. Yeah. Okay, so if we just went back to h down there, so like if we, yeah, so instead of doing that pattern matching, if we just go back to h equals question mark, then can we just return underscore comma h? Yes. Okay, good point. I like that. Okay, what about the z case? In the 0 case, what we know is that a black node, well, it's, yeah, it is the same. But let me just talk through this because it's going to introduce a new feature, which is what we know is a black node has black height 0. Can a black node ever have black height 0? No, because a black node has black height at least 1. So if we case analyze h here, what will happen is that Agda will fill in what's called an absurd pattern, open paren, close paren, which means this can't have happened. Okay? And when you have a situation that's absurd, where it can't have happened, then what you get is just you don't have to fill in the right-hand side. That case just gets crossed off. Okay? Okay. if this seemed a little bit circuitous, then that's okay. So this approach I was taking here, where we case analyze the simply typed data and then invert the derivation, is a little bit weird, because in the empty case, we didn't use n and h. In the next case, we looked at some stuff. In the next case, we looked at the color, though we didn't really need to. Thanks for pointing that out. OK, so what I wanted to do is get to a slightly nicer way to write this function, which is if we get back to the beginning, where we just have, we're trying to prove black and root black height of t, n, and h. And if you rename that to black and root black height 2, OK, t, n, h equals question mark. OK, so now what we can do is instead of analyzing the simply typed data, we can analyze the dependently typed data. And that will tell us what the simply typed data must have been. So if we case analyze h right here, OK, let's case analyze h right here. It says, oh, OK, you have these cases for empty and a red node and a black node and 1 and n and successor of n and HBH empty, HBH node red, HBH node black. OK, and the nice thing here is that when we inspected the derivation, Agda filled in what happened with the subjects of the derivation. So it's often the case that you should think about case analyzing dependently typed data first and looking at simply typed data second. OK? OK, so let's see. And then the right-hand sides of these are going to be exactly the same as the one above, so let's not even fill that in. Let's go on to the next thing. OK, so we started about 10 minutes late, and I want to have about 10 minutes more of stuff so that there's some exercises in the hands-on stuff that we can get to. So everybody good with this? Make sense? OK, so now let's go on and do another version of the data type. And what I want to illustrate here OK, so what I want to illustrate here is it's kind of annoying that we have all of these like underscores sitting around everywhere when we make these derivations. So we can use an Agda thing called implicit arguments to get around that. OK, so the idea with implicit arguments is that if we take our data type and copy it down to implicit args, we're going to make it so that we don't have to write those pesky underscores all over the place. And the way that we're going to do that is we're going to change the the parentheses x colon a dot b to curly braces x colon a arrow b. OK? And the thing with the curly braces is it's semantically exactly the same kind of thing as the other dependent function type. But by default, Agda inserts an underscore. OK? So if we write our data type like this, then we can try to prove black and root black height for this definition. OK? And when we try to prove black and root black height for this definition, let's grab, just grab the type, and then we'll fill it in. Yeah. OK. So when we try to prove black and root black height for this definition, and let's make t and n implicit arguments to the function as well. So the implicit arguments just mean I'm not going to write this. So nothing different is going on semantically. I'm just not going to write it in the text. So it looks like I just have an argument. Don't copy it. We'll just do it. Yeah. OK, so now let's just case analyze h. So we have this h. Implicitly, we also have t and n, but we don't see them. So we case analyze h. Hey, that looks nicer, right? Now we don't have all of the gobbledygook sprinkled around it. And now in the right-hand side, we can fill in underscore, comma, HBH empty. And in that one, and then in the next one, we'll start to see a little bit of a difference. In that one, it'll be underscore, comma, Yeah. And now it's just HBH node black of H and H1. Okay. And then the same thing should fill the next hole. Okay. So when you have implicit arguments, there's a lot going on behind the scenes. There's a lot more going on in this function than you actually see in the text, right? The text is really nice and short. It just says, hey, I applied this inference rule, empty. Turn that into this inference rule, empty. It says, I applied this inference rule, HBH node red, turn it into HBH node black applied to the two subderivations, okay? There's really nothing different, though. If we wanted to grab the name of the number n, then in the pattern HBH node black, we could have written curly braces n. Okay? So if you want to explicitly bind a name for an implicit argument, you can do that by writing a curly braces application. Okay? And then over there in the right-hand side, we can now say that that first underscore in that line is, in fact, going to be successor of n, right? Because that's what it turned out to be. When you make a black node black, it's still successor. And if we wanted to apply HBH node black on that side to n, we could do that like that too. So really, there's nothing going on with implicit arguments. It's just changing the defaults. It's like inserting underscores everywhere, except it really cleans up the text of the program in order to, if you can not see that. OK. Good. So I think that's a good stopping point for today. There's a few exercises in the hands-on session that will, so in your code, you have a file called handson.lab1, which has the exercises that we'd like you to work on either in the next little bit or sometime tonight. Okay? There's a few exercises at the end, the one about